Therefore, we have the following, which is the same value in table 1.4 for E of 111 and E of 100. For iron, we have this expression, E of 110 is equal to 210.5 gigapascals. No idea where we're getting that from. We have some other things that would be good to look at. Example, note that E111 is greater than E110 is greater than E100, and that E110 is in good arrangement with the average value of E, modulus Young's elasticity, for the polycrystalline sample, table 1-1. For the case of tungsten and any other isotropic material, then we have equation 1-15. If we compare equations 1-15 with equation 1-10, the elastic constants, S sub ij, may be described in terms of the familiar strengths of material elastic constants. Therefore, equation 1-16, A, B, C. Finally, from equation 1-16, we have the following expression, and we have equation 1-16b. For the case of hexagonal crystals, the matrix in equation 1-11 reduces to equation 1-17, where L sub 1, L sub 2, L sub 3 are direction cosines for directions in the hexagonal unit cell. From equation 1-17, note that in hexagonal crystals, E depends only on the direction cosine L sub 3, which lies normal to the basal plane. Consequently, the modulus of elasticity in hexagonal crystals is isotropic everywhere in the basal plane. 1.2.1.2, resiliency. The resilience of a material is the measure of the amount of energy that can be absorbed under elastic loading conditions, and which is released completely when the loads are removed. From this definition, resilience may be measured from the area under the curve in figure 1.1. Equation 1-18, where sigma sub max is the maximum stress for elastic conditions. Epsilon sub max is the elastic strain limit. From equation 1-7, we have equation 1-19. Should an engineering design require a material that allows only for elastic response with large energy absorption, such as in the case of a mechanical spring, the appropriate material to choose would be one possessing a very high yield strength with low modulus of elasticity. 1.2.2, elastic homogeneous plastic response type 2. When a material has the capacity for plastic deformation, irreversible flow, the stress-strain curve often assumes the shape of curve 2, figure 1.2. Here we see the same elastic region at small strains, but now find a smooth parabolic portion of the curve, which is associated with homogeneous plastic deformation processes, such as the irreversible movement of dislocations in metals, ceramics, and crystalline polymers, and a number of possible deformation mechanisms in amorphous polymers. That the curve continues to rise to a maximum stress level reflects the increasing resistance on the part of the material to further plastic deformation, a process known as strain hardening. The portion of the true stress-strain curve from the onset of the yielding to the maximum load may be described empirically by the relationship generally attributed to Hallam. Equation 1-20, where sigma is the true stress, epsilon is the true plastic strain, n is the strain hardening coefficient, k is the material constant, defined as the true stress at a true strain of 1. However, Bulfinger proposed a similar parabolic relationship between stress and strain almost 200 years earlier. The magnitude of the strain hardening coefficient reflects the ability of the material to resist further deformation, and may be equal to unity, which represents ideally elastic behavior, or equal to 0, which represents an ideally plastic material. Selected values of strain hardening coefficients for some engineering metal alloys are given in table 1.5. Note that n values are sensitive to thermomechanical treatment. They are generally larger for materials in the annealed conditions and smaller for the cold work state. Such data may be derived by plotting true stress and associated true strain values on log-log paper. If equation 1-20 was absolutely correct, a straight line would result with a slope equal to n. However, this is found not always to be the case, and reflects the fact that this relationship is only an empirical approximation. When a nonlinear log-log plot does result from a given material, the strain hardening coefficient is often defined at a particular strain value. In general, n increases with decreasing strength level and with decreasing mobility of certain dislocations in the crystalline lattice. More will be said about this material property in Chapter 3. 1.2.2.1, Strength level in materials. It has become common practice to define several strength levels that characterize the material's tensile response. The proportional limit is that the stress level below which stress is proportional to strain, according to equation 1-7. Remember, equation 1-7 is important. The elastic limit defines the stress level below which the deformation strains are fully reversible. In most engineering materials, these two quantities are essentially equal. However, it is possible for a metal to exhibit nonlinear but elastic behavior. For example, very high strength filamentary particles, often called whiskers, can exhibit elastic strains in excess of 2%. In this range of very large elastic strains, the modulus of elasticity reveals its weak dependence on strain, something that is completely obscured when strains are very small. For example, note that dF divided by dx in figure 1.2b decreases with increasing distance of particle separation. As such, Hooke's law, equation 1-7, represents an empirical relationship, albeit a good one at small strains. Consequently, the elastic limit is approximately equal to the proportional limit and may be slightly higher in some cases. A much more important material property is the yield strength, a stress level related to the onset of irreversible plastic deformation. This quantity is difficult to define, since the point where plastic flow will depend on the sensitivity of the displacement transducer. The more sensitive the gauge, the lower the stress level where the plastic flow is found. In recent years, special capacitance strain gauges have been used to measure strains in the range of 10 to the negative 6. In fact, a number of studies dealing with the mechanical behavior of materials in the microstrain region have been undertaken as a result of this breakthrough in instrumentation. These investigations have shown, for example, that plastic deformation, the irreversible movement of dislocations, occurs at stress levels many times lower than the conventionally determined engineering yield strength. To arrive at a uniformly accepted method for determination of the yield strength, therefore a standard test procedure, ASTM standard, has been adopted. The yield strength value is obtained in the following manner. 1. Determine the engineering stress-strain curve, such as the one in figure 1.6. 2. Construct a line parallel to the elastic portion of the stress-strain curve, sigma-epsilon curve, but onset from the origin by a certain amount. The generally accepted offset is 0.002 or 2% strain. And 3. Define the yield strength at the intersection of the stress-strain curve and the offset line. As cited above, this value is usually defined as the 0.2% offset yield strength. The ultimate tensile strength is defined as the maximum load divided by the initial cross-sectional area, while the true fracture stress is the load at fracture divided by the final cross-sectional area with correction made for any localized deformation, necking, in the final fracture region. A compilation of tensile properties for a number of engineering materials is given in tables 1.6 and 1.7.